For building materials that will prevent fires. So fire suppression, flame retardancy is the focus of my presentation. And these days in engineering, we usually start with our acknowledgements, and I have a very good research team at Texas A&M University, and I have wonderful collaborators around the world. You can see some of them listed here on this slide, and I've got some good financial supporters through the U.S. government, but also through a number of industrial sponsors. And of course, we're always open for other sponsors as well going forward. In my research group, flame retardancy is one of several topics that we focus on. It's probably become the biggest thing that we're working on these days, but we do a lot of gas barrier and gas separation work, and we also do some work on alternative energy, specifically thermoelectric materials. But today, of course, the focus will be flame retardant treatments for various materials. On a broader scale in my research group, we focus on polyelectrolyte complexation, polymer particle interactions, water-based processing, and renewable chemistry. So you could call it kind of green research that we're doing. So here's the outline that I'll follow. I wanted to first just talk about fires in general and the need for flame retardant materials. And then I'll talk about three different specific topics. So I live in the United States, so of course my statistics are focused there, but you can see that just the US suffered $25 billion in fire damage / loss in 2018. I think this Grenfell Tower fire in London in 2017, of course, many people knew about it. And then the Notre Dame Cathedral just 2 years ago had a severe fire and is probably going to take 20 plus years to fix, or maybe 50 years to fix. One issue with current flame retardant treatments is that a lot of them are using these brominated or halogenated compounds, and there's a lot of concern about toxicity, poisoning groundwater, creating disease in humans, etc. In the United States, we've been having fires in wine country. This is in Napa, California, just less than a year ago. They were having severe fires, and then I know in Australia they've been having severe forest fires. And then this picture that I just flashed up here is actually from the state of Washington in the northern United States. Also was having major forest fires last year. So in my own group, we're very active on this topic of flame retardant treatments, surface treatments. And this is just an example of some of the papers that we've published recently. We have two big technologies that we've developed over the past decade. One is focused on what's called layer by layer assembly. And we published a review paper 3 or 4 years ago. And you can see here, it was in Journal of Material Science. Just last year, less than a year ago, we published a broader review of flame retardant surface treatments that covers all sorts of surface treatments to flame retard foam, fabric, building materials, etc. In terms of the layer by layer assembly, it's a water-based coating method where we take cationic and anionic ingredients and deposit them from water into these very thin layers. The criticism of this technology is that it's a multi-step deposition process, sometimes tens of steps or even hundreds of steps to build the functional coating that you want. Some of the ingredients that we use are shown over here at the right. You can see you typically have nitrogen-rich and phosphate-rich molecules which serve to create an intumescent type of treatment, which bubbles and creates an insulating char. Many times we also incorporate nanoparticles such as clay nanoplatelets to reinforce the char that forms during burning. and stop fires. So it's a very flexible technology, but once again, people criticize the number of processing steps. Specifically for wood, wood is a very complex structure, as many of you may know. It's a cellulosic material. Of course, it's very flammable. It's a nice building material, though. In the United States, we still build houses with wood. And I know a lot of countries in Europe, especially, brick or cement are becoming more common than wood for building a building. But anyway, we can put layer by layer onto this wood, but it would take days to get a good coating because of the difficulty. On flexible polyurethane foam, it's also used in upholstered furniture, and throughout the world it's used for seating in automobiles, etc. It has a big problem with flammability and melt dripping. We've successfully flame retarded flexible polyurethane foam using layer by layer assembly, but also using polyelectrolyte complex coatings, which are much faster and easier to deposit, as I'll show later. I may not have time actually for the foams, but I'm just mentioning that we are able to flame retard. You can see this publication at the bottom highlighting that. And then very recently, we began to look into fused filament flame retardancy because of all the work being done nowadays in additive manufacturing. In my own university, our 3D printing laboratory actually burned down. So once again, these filaments are very flammable, and they're being processed under hot conditions, and there's a great chance of fire. So if you could produce flame retardant filaments, it would really help the additive manufacturing community. And so this is something I'll highlight. So getting away from classical layer by layer assembly, we began to look at these polyelectrolyte complexes, and you can see what happens if I have a positively charged and a negatively charged polymer or polyelectrolyte. They will want to complex with each other. And so you need a high charge density in the molecules to get this complexation. But I also need to be able to process a stable solution from water and then apply this complex to a surface. So what we do is we use weak polyelectrolytes so that we can adjust the pH just before we form the complex. And the pH adjustment will create the complex. Therefore, we can coat a material and then adjust the pH, and then we will have the complexed coating that is flame retardant. So I'll highlight this in 3 applications. The first is textiles. So cotton, of course, is the most used textile for clothing. And so we can use something like polyethyleneamine and pair it with sodium hexametaphosphate, but we keep it at a pH where they will not complex. I purposely keep PEI at a high pH so that it has low charge density. But then when I reduce its pH below 9, a complex will form because the charge density of PEI will increase. So in this example, I take cotton fabric, I dip it into this polyelectrolyte complex suspension. PEC means polyelectrolyte complex. And then when I, as a second step, dip that same textile into a buffer solution, here it shows pH less than 6. It would depend on the chemistry that you're working with. But in this specific PEC, the pH 6 buffer caused the complexation on the textile to make a very uniform, conformal coating on the cotton. And then, so if we take a look at the uncoated cotton, of course, this is a vertical flame test that I'm showing. It's ASTM 6413 is the standard vertical flame test. Cotton is completely consumed, of course, by the fire without any treatment. If I apply my polyelectrolyte complex, but I don't use the buffer to lock in that complex on the textile, I'll get a lot of char, but this is not considered a passing vertical burn test. But then once I cure, we call it curing with the buffer, when I lower that pH, I get a highly ionically cross-linked conformal coating on the cotton, and then we pass the vertical burn test. You can see that some char forms, but then the rest of the fabric is unharmed because the intumescent action of that coating self-extinguishes the fire. Cotton is actually very easy to flame retard, so I always say you could spit on cotton and pretty much make it flame retardant, so that's not a big accomplishment. Nylon and cotton, which a lot of clothing is usually a combination of polyester, nylon, and or cotton. So nylon cotton is very challenging to flame retard because cotton combusts, nylon melt drips and burns much hotter than cotton. So it's a bad combination in terms of fire, those two chemistries. So we had to modify our recipe. So we took a very similar polyelectrolyte complex. We still dipped it into the buffer, but before we did the buffer curing, we added a melamine solution so that we formed melamine polyphosphate in situ. It's a water-insoluble molecule, but we formed it in situ on the textile itself prior to complexing. And then now if we look at the vertical burn of nylon cotton, if there's no coating, you're going to see that in this video, it's burning much more vigorously than the cotton was burning. You can see how bright that fire is and how aggressive it is. But in the complexed coating that has the melamine, you can see it added 19 weight percent. The coating added 19 weight percent to the textile, but it created this self-extinguishing effect, and it passed the ASTM 6413 vertical flame test. And so we looked at different melamine concentrations, and it turned out above a 2% in water melamine solution, there was no need to go higher in concentration. But anyway, this was a nice demonstration of a very simple coating that could be deposited commercially using pad dry processing, the same process you would use to put dyes, for example, or water resistant treatment onto a textile. You could use the exact same processing equipment. I mentioned wood was hard to coat with layer by layer assembly, and so we used polyelectrolyte complex coating instead. Here's PEI, here's sodium hexametaphosphate. I've already introduced these molecules. And then what you can do is you can soak wood into this PEI PSP solution and cure it with this buffer treatment, just citric acid in this case, just like we did with the textile. And then you get a flame retardant wood created in this process. And so you can see that the coated wood maintains all the same aesthetics. You wouldn't know that there was a coating visually. And then we can see the weight gain of various dipping times and curing times. That means the amount of time in the polyelectrolyte complex and the amount of time in the buffer solution. I should mention, if you were to use pressure treatment or modern wood processing treatments, you could actually dramatically reduce these times. These are long times because we are doing it in a laboratory without wood processing equipment. This is just proof of concept. But anyway, if you look at wood after coating, you don't see any difference in terms of the nano microstructure. And then if we hold a torch for 45 seconds on the wood, you can see that it only forms char, it does not catch fire. But the uncoated wood, of course, burns up completely. So below you can see we are looking at after flame time of the wood and the residue of wood that's left behind. And you can see the best coating that was only adding 6 weight percent to the wood maintained a 90% residue, which means basically the wood didn't burn. And so we can look with EDS to see how deep did that polyelectrolyte complex coating go into the wood. And it looks like in the best coating, it went about 1 millimeter deep. So we didn't even need to fully coat all the wood. Just the surface 1 millimeter of the wood provided tremendous flame retardancy. And so here we're looking at TGA, or actually micro-cone calorimetry, which is a lot like a TGA. And you can see time to ignition, peak heat release rate, total heat release, total smoke release, etc. And if we compare uncoated and coated, you can see time to ignition takes longer, peak heat release rate is reduced, total heat release is reduced, and the residue, it goes up dramatically because of this coating that we, and then if we look after burning on the coated wood, you can easily see this intumescent bubbling. So there is an intumescent effect going on here. Gas is released from the coating and it creates these insulating bubbles of char. To my surprise, it turned out that we actually got, the wood became stronger as well. So if we look at the flexural modulus and flexural strength of the wood after that 6% coating, you can see that you had a 25% increase in strength and a 71% increase in modulus. So that's quite interesting. It's probably mostly because you had some densification of the wood upon coating. But as I showed in the microscope images, it was still conformally coated and the wood still had its porous structure, but certainly the coating adds a little bit of density, and I imagine that contributes to the improved strength that we're seeing. So it's a nice side effect, unintended beneficial side effect. Finally, I wanted to mention the fused filament 3D printing. And so in this case, we took polyvinyl amine and made a complex with sodium hexametaphosphate, the PSP that we've seen before. And then we blended this complex with polylactic acid. PLA is a very common 3D printing filament. And when we made this combination filament that had the polyelectrolyte complex plus the polylactic acid, first I'll show you just the burning of I wanted to highlight the burning of the complex itself. So that's just the powdered complex, and when you hold a torch on it, you can see that it turns black and bubbles up. So it definitely is showing you the intumescent behavior. But when we make a filament that's 75% PLA and 25% complex, it can be printed exactly the same way that the normal PLA filament is printed. And so, of course, we have to print the T of Texas A&M University here, and we're looking at the PLA-T and the T that has the 25% of polyelectrolyte complex added to it. And so you actually get higher crystallinity. We actually think, once again, much like with the wood, you actually get a stronger part created because of the polyelectrolyte complex being present. Now, when we look at microcombustion calorimetry, known as MCC, it's like a small cone calorimeter. You can see the char yield. The PLA has no char yield, and you get 13% with the combination filament. And then dramatic reduction in peak heat release rate and significant reduction in total heat release. And then in these videos, you'll have a chance to see the difference. So the PLA object, when a torch is held on it, melt drips and completely burns up, basically. But that melt dripping also spreads fire. You can see the other T, it just self-extinguishes immediately. When the torch is removed, there's no more burning. And you can see how it intumesced, it bubbled up where the flame touched the T. So truly, it worked very beautifully. So this is a new, relatively unique new area for us. It's an extension of our layer-by-layer work that we had already been doing for many years. The PEC technology we've been working on for 5-6 years now. Layer-by-layer we've been doing for 12+ years. But you can see that we improved the strength of wood and made it flame retardant. Same thing with filament. And then textiles, it's a very simple treatment that could be done via head dry processing. Going forward, of course, we want to get rid of that buffer treatment. We'd like to combine the solutions in a way that would allow us to, in one step, make a very good coating instead of 2 steps. Of course, make it easier. In terms of wood, we want to look at other properties that we can add to the PEC, like antifungal. And then with the fused filament, with the filaments for 3D printing, we want to look at other chemistries. PLA is the easiest filament to flame retard. Now we want to move on to nylon, which would be very valuable to various industries that are printing prototypes and things such as that. So with that, that's the presentation.